Okay, so welcome again in this 18th lecture in which I will keep working on the torsion problem. It's a very important problem for the theory of linear and nonlinear elasticity. So this is just to recap, lecture 18. So as you see here, I have already reported the calculations from the past lecture. All these calculations lead to a form of the stress which is, in fact, if you look at it very carefully, very similar to the stress components of simple shear. There will be some surprise here. We'll discuss it shortly. So again, from all the computations I have done from the previous lecture, continued from the last lecture, the stress components are the ones that you see here. Now, so essentially what is that I want to do? Well, just let me make maybe just a very little premise. What I'm doing here is I'm studying the problem of torsion of a cylinder, and the cylinder is being subjected to a state of deformation where the angle between the lower base and the upper base is where the angle between the upper base and lower base is described by this deformation. Essentially, if you remember, the deformation here is described in the following way. The radius remains the same, the height remains the same, and what changes is the angle. So the angle in the current configuration is equal to the angle in the reference configuration plus an angle plus a quantity d times the height z. Okay, so in other words, what does it mean? Well, that if you imagine this cylinder made of discs, each of these discs rotates with respect to the lower one of a quantity dz. In other words, if you imagine, for example, that this little piece of cylinder has a height equal to 1, imagine the height of this is equal to 1, well, essentially the rotation of the upper with respect to the lower is defined by d. So if this let me say angle here, so imagine that the green segment in the reference configuration becomes, in the current configuration, this helix here, and so essentially you see there is a rotation. I fell my pen. I lost my pen. So imagine once again, by repeating the little drawing that I did in the previous lecture. So essentially what was initially along this straight plane here is deformed into this helix. Well, then the angle between these two lines, so essentially this line and this line, this angle here, you see what is it is written here. So this tells you the rotation of a cross section with respect to the non-rotated configuration. So the rotation of this surface, this would be equal to the rotation essentially is given by dz, but since z, the height, is equal to 1, then this angle is essentially measured by d. So in other words, this is the experiment that I'm doing, and I'm trying to compute all the forces that built up in the cylinder when applying this torsion. So essentially this D is in fact measuring the amount of twist that you are prescribing on the cylinder. So the reason for which I want to compute the stresses is obvious, because I want to compute what is the torque and that produces this type of torsion. But you see, in order to do so, we have to compute, in these expressions here, everything would be known, because once I give you the energy, The deformation is completely known, so the energy is completely described in terms of deformation. So if D is prescribed, all of these guys here are completely known. You see all the things that are included in these in these terms are completely known. There is only one problem, that I still don't know what is the value of the pressure, and for this reason we have to impose equilibrium. So let us impose equilibrium. So in these expressions, let me just mark down in these expressions, P is unknown, and to find it we need to impose equilibrium. So let us impose equilibrium. How do we impose equilibrium? Well, as usual, equilibrium is imposed by writing that the divergence of sigma is equal to 0, okay? So, of course, this is a tensor and this is a vector. Now, again, we have to do this. You know how to do this in Cartesian coordinates. These you have seen with Michel how to write these in Cartesian coordinates. To write this in, we are working in cylindrical coordinates, and so for this reason we have to be able to write this expression in cylindrical coordinates. And now, once again, to do this equation in the cylindrical coordinates, you would need some intermediate passages which are not completely immediate. And for this reason, don't worry, because in an exam paper, okay, once again, this year there will be the notes, but in general, we prescribe that. Just as I gave you the form of the gradient of deformation, I will give you now the expression of this divergence when this is written in cylindrical coordinates. So, of course, it boils down to three equations. Let me write down these equations. So, the first is that the derivative of the sigma r component plus 1 over r, the derivative of sigma r theta relative to theta, plus sigma r minus sigma theta divided by r, plus sigma derivative of sigma r z relative to z equal to 0. So this is the first equation. Don't be scared. You don't have to remember these things by heart. We give them to you, and in any case you have them on your notes. So this is the first equation. So this would be the radial component. So because of course this is a vectorial equation and it is projected in three directions, and this is the radial component. Now this is what is called the hoop component, which would be the component along the unit vector in the hoop direction, and this expression of the equilibrium equation reads as follows: the derivative of sigma theta r relative to r plus 1 over r, the derivative of sigma theta with respect to theta, plus 2 over r sigma theta r plus the derivative of sigma theta z relative to z equal to 0. So this is the second equation. And finally, the third equation is that the derivative of sigma z r relative to r plus 1 over r, the derivative of sigma z theta relative to theta. I'm copying as well. It's not that I know this by heart. You don't have to know these things by heart. Plus sigma zeta zr relative to r, and plus the derivative of sigma z relative to z equal to 0. Okay? So these are the three equilibrium equations. And now, these three equilibrium equations, what do we need these equations for? Well, essentially now we have to take the expressions that we have obtained in the last lecture for the components of the stress, and we have to impose equilibrium. Okay, so I forgot to say this is the component of and the last one is the actual component of the stress of the equilibrium equation. Okay, so when we take the components of the stress and we use the equilibrium equations, so essentially take these equations here. There is missing something here because I realized that it's missing the component Rz. You can just obtain it very quickly, and this is required for, you see, it shows up here, for example. So you need to compute this, it shows up here, so you need to compute it, but it's rather easy. I strongly suggest that you do this as an exercise to practice a little bit. So when you do this, then these three equilibrium equations finally reduce to this very mild form, and they reduce to, finally, we obtain the following. So when imposing equilibrium, we get minus the derivative of P relative to R plus 2 derivative with respect to R of W1 minus W2 minus 2D squared R W1 equal to 0. This is the first equilibrium equation. I will make a remark now, and the other two are very simple because the other two are dP in d theta equal to 0 and minus dP in dz equal to 0. So you see, there is a strong advantage, of course, let's say at least in the end things get very mild. I only want to make a little remark here. If you notice, I didn't use a partial derivative, but only used an exact derivative. The reason is that if you compute the invariants I1 and I2, in this problem, you will discover that the two invariants I1 and I2 of the tensor B, they're both equal, and they're equal to 3 plus d squared r squared. In other words, the two invariants, they only depend on r. They do not depend on theta and on z. So for this reason, this guy, which comes from here, which comes, from this first piece here, the partial derivative becomes a differential, simple derivative, an ordinary derivative. This is the first observation that I want to do. The second observation that I want to do is, remark, well, in fact, from these two equations here, we have equation 1, equation 2, and equation 3. We see that from 2 and 3, we see that the pressure should not depend on theta and z. Because, of course, if the partial derivative with respect to theta and z is equal to 0, this means that P is only a function of r. So this actually means that the first equation, equation 1, can be actually rewritten in a different way. And how do we obtain P at this point? Well, let me just copy this equation here and pass to the next page. So I've just copied the expression, the equilibrium equation in the radial direction. And remember that we're doing all this to compute the pressure. Once we know the pressure, we know all the stress components. And from this expression, as I told you before, this actually can be rewritten as P prime R, yes, because it's just a simple derivative relative to R. So in other words, if we bring it on the other side, we can rewrite this as the derivative of P of R with respect to R. This is equal to, well, I just have to bring it on the other side, so this becomes 2, the derivative relative to R of W1 minus W2 minus 2 d squared R W1. Don't forget, once again, as a remark, as I said in the previous slide, that all these guys functions of R, okay? Well, at this point, I need to compute P. What I can do, I simply integrate this expression. So let me integrate this expression relative to R, and in fact, we can obtain at this point that P of R is equal to what? Well, first of all, there will be a constant of integration. Let me just call it C. And then I will have, well, here there is just the integral over derivative. So this is simply equal to 2. And let me simply write W1. I want to stress the fact that these are functions of R. So minus W2 of R. And here I have to integrate and we have to decide from where, but in fact let me just write generically. This would be, because I'm not specifying the boundary conditions actually, so let me just say this is simply the integral. Well, actually, you see here the 2d squared, this is a constant, I can shift it outside of the integral, so this becomes 2d squared, and here I have the integral. I should use R, but in fact, to stress the fact that this is an independent variable, let me just use X. So it would be X times W1 of X, okay, in the X. It's just the same. And then evaluated in R. Okay, so we have found the pressure, and once we found the pressure, we can actually compute all the stress components. Now, once again, this C that appears in this expression is an integration constant. Integration constant. Okay, so how do we compute the stress components? Well, the stress components are rather immediate to compute because we obtain that the sigma RR of R, I should just use the components that I wrote in the previous lecture. So we'll just copy it here again. This is equal to minus P of R. And then, if you remember, this is just what we have obtained in the last lecture, minus 2W1 of R minus 2W2 of R. And then if you replace the expression of pressure computed there, we obtain that the sigma RR component, well, in fact, it's rather simple because please note that P has this term, which is precisely this term. You see, so when I bring P on the other side, I get that this minus P plus this guy is equal to, well, there will be this guy go on the other side, and then there is the integration constant. So essentially, this reduces to 2d squared, the integral evaluated in R of x W1 evaluated in, so this is this integral plus the constant of integration. Okay, so essentially now we essentially now need only to compute the C, and to compute C, we essentially need to fix a boundary condition because, for example, so far we didn't say nowhere that we're not squeezing laterally the cylinder. In other words, if you take into consideration the cylinder, so if this is the cylinder, the sigma RR component of the stress is the component that refers to this external mantle of the cylinder. So, well, not external, but if we evaluate it externally, this would be what? Sigma RR evaluated at the external radius, which is, let me say, A. So, what does it mean? Well, since we're not squeezing the object, imagine that with my little hand I'm pushing laterally, this would exert a component of traction in this direction, but we're not doing anything like that. So, this means that since the external mantle of the cylinder, so since the external mantle of the cylinder is stress-free, actually I should say is traction-free, we need to impose the following boundary condition. We impose the boundary condition that sigma RR evaluated at the external radius of the cylinder A must be equal to 0. So if I do so, this reads to d squared integral, but now I have to compute it in A, and of x w1 x in the x plus c. So from this expression we get that the unknown constant c is equal to minus 2d squared integral. You see, I'm not specifying the lower bound of this integral because in fact it is not important. As you will see now, we could put any number there, but you will see this now. Imagine there is just any number. So this becomes the integral from any number to a of x w1 of x in dx. And if at this point I replace this into the expression of the stress, when I do, you see this integral here minus, which means plus c, so minus this integral, then of course the sigma RR component immediately becomes sigma RR of R is equal to, well, this becomes 2d squared integral from R, from A to R, because this minus, essentially, it's this integral here becomes 2d squared integral from A to somewhere of x w1 x in dx, okay? So this becomes the integral from A to this of x w1 x in dx. And we finally have computed the component of sigma RR. So if you give me the amount of twist, so essentially what is the amount of twist? Again, if I know that the upper surface initially was imagine you make a dent on the upper surface there, and then after rotating the upper face there is an angle, it creates an angle. This angle for an height of the cylinder equal to 1, this angle is equal to d. This is the meaning of this d. It would tell you of how much the upper surface of a cylinder of length 1 rotates with respect, for example, to the lower base, and this is the definition of amount of twist. So you see in this expression, W1 only depends on R, so you can, and on D, you can integrate this. D is prescribed, and from this expression, given D, you can compute sigma RR, okay? So you see this expression can be used to compute from D given, which is the twist of the cylinder, you can compute the tension. Likewise, from the same components, the same expressions I gave you initially, you can compute all the other components of the stress. So you can compute the sigma R theta, you can compute the sigma ZZ, and you can compute all these quantities. You just have to plug in these expressions. Now, what do we use these for? Okay, did I tell you in the beginnings, when I subject this cylinder to torsion, I'm doing something. I'm holding the height fixed. So if the cylinder, for example, wants to elongate, what do you think it will happen? It is exactly like the same effect that you have seen in simple shear. If you keep the height of this cylinder fixed, if it wants to elongate, you will find the air compressive forces on the upper and lower bases. So let's try to see if this is the case. So imagine you have computed the sigma, all the components of the stress, and you want to compute the force emerging on the upper and lower bases. So what I want to do is to compute the axial force exerted on the basis of the cylinder. So how do we compute them? Well, let me just make a little scheme here. So imagine this is the upper face, essentially the component sigma ZZ tells you what is the stress in a small neighborhood. So if you take a small area here, and this small area is the A, then the component sigma Z that we compute from there is just it's a tension. Yes, it's not a force. So it expresses essentially a force per unit area, okay? And furthermore, I should be more precise here. It doesn't really make a difference because in this case, this surface is not changing area from the current to the reference configuration, but I should be writing actually the lower A, because I'm integrating on the current configuration. So let me say that this is the A. So essentially, to compute the normal force, the total normal force that I would experience on the upper basis of the cylinder, I'm not drawing the rest of the cylinder here. So when I want to compute the total actual force that is exerted on the upper face, so let me just denote this force as N. Now this is a force, okay? So N is a force. Sigma ZZ is a tension. So what I should do is should simply integrate on the upper face. Let me call this phase, I don't know how did you call it with Michel, but let me just call this phase, I don't know, omega. And I should integrate on this phase sigma ZZ in dA, right? But in fact, if you remember that this dA is just the elementary area element here. Now, what is this dA in this case? Well, if you remember from this is from classical calculus, this dA is very easy to be deduced, because if you take a little wedge of a small angle here, well, this dA is in fact, if this small edge has an angle alpha, then, and this is located at a radius r, then and this is a small dr, then this small element of area is equal to alpha times r times dr. And however, since in this case this is sigma ZZ, you see it only depends on r, you can integrate on the angle, and this alpha here becomes 2 pi. So in other words, this simply means that when you do this integral here, this is simply this becomes 2 pi r times dr. Okay, and then we simply have to do this integral from 0 to the external radius a of sigma ZZ r times 2 pi r dr. Okay, now it's not that I want to bore you with this calculation. I want to give you directly the result, but it is important that you go through this result. Also in the notes you will find all the details. In the typed notes you find all the details of this calculation. When you compute these, do it also because in a written exam we would ask for the intermediate passages. When you do this, you just have to plug in this expression, the expression of sigma ZZ that you have deduced. Then you get that this is equal to minus 2 pi d squared integral from 0 to a of r cube. And here we have W1 plus 2 W2 in dr. Okay? Now, still it's not... so, question. If you remember, the experiment we're doing is we're twisting the cylinder, we're holding the height fixed. So question, what is the sign of this force? If this force is in this direction, then it means that the cylinder wants to shorten. And let me explain this better. So imagine that the cylinder was let, if the cylinder is let free to deform, which means I'm not holding it actually fixed, okay? When I twist it, imagine that the cylinder elongates. If the cylinder elongates, then to bring it back to the original height, which is this, yes, what I have to do, so imagine this is the twisted cylinder in which I've applied a torque. I've applied the torque here, and I've applied the torque below. But then, To bring it back to the original height, what I have to do is I have to apply forces, and these forces have to be compressive. Okay, so this is the idea that I'm using here. Sorry for the bad drawing, but it's just a little scheme to understand what is happening. So essentially, the point is that I am applying a twist on the upper and lower faces of the cylinder. However, at the same time, I need to apply a compressive force. And this compressive force is the one that opposes to the elongation. However, so the question at this point is this quantity negative? So if this is true, so as we have seen in this little thing, if the cylinder elongates in torsion, then n should be lower than 0. Now, it seems there is a little minus sign here, but it's not enough because we don't know if the sign of this expression is actually positive or negative. Now, in fact, if you take a Mooney-Rivlin material, so imagine you take a Mooney-Rivlin material, so we need to make an example, and this is very similar conclusion that you have deduced with Michel in the simple shear. Take a Mooney-Rivlin material. Well, for a Mooney-Rivlin material, the energy, as you remember, is written as C1 divided by 2 times I1 minus 3 plus C2 divided by 2 I2 minus 3. Well, then in this case, you immediately see that here W1 is actually just a constant, and this is equal to C1 divided by 2. I just remind you that W1 means the derivative of these relative to the first invariant, and likewise W2 is just equal to C2 divided by 2. And with this in mind, I can just enter the expression of the axial force, and I can compute what is this equal to for the Mooney-Rivlin material. So for a Mooney-Rivlin material, we get, finally, that the normal force that it has to be exerted on the upper and lower face is equal to minus 1/4 times C1 plus 2C2 times pi a to the 4th power d squared. So what is this expression telling you? Well, in fact, C1 and C2 can be extracted from experiments, but from experiments, at least for example, for all ordinary materials, you can find that this quantity from experiments, these are generally positive. So since there is this beautiful minus sign, we get this is lower than 0. So this is the proof of the fact that when you subject a cylinder to torsion, in fact, the cylinder, normally it would elongate, but since the experiment, the description that we did was such that the cylinder height was kept fixed, then there should be a normal force. And in fact, we've proved that this normal force is compressive, proving that in the absence of such force, the cylinder would otherwise elongate. So this effect, once again, was discovered by Henry Poynting, that you may already have encountered in electromagnetism. He is exactly the same guy, and in 1909 he made this observation. Actually, he did this for not for soft materials initially. He did it for steel cables, but eventually it proved right also for rubbery materials. I just want to mention that remember that in all this discussion, the twist is fixed, which means this d, the amount of torsion, this d here is describing the amount of twist. Okay, so it's essentially the variable that you are controlling. Okay, amount of twist. However, you may also wish to compute, for example, what is the torque applied on the upper face. And if you want to compute the torque, I will just add this little note at the end. If you want to compute the torque on the upper face, then what you should do, I will just redo the same drawing I did there. So essentially, if I draw the upper face of the cylinder, now if I draw once again this little elementary area, the tension that we need to compute and we need to take into consideration is the one giving rise to the torque, which would be the component of the stress vector along the tangent plane. So essentially it would be the component sigma z theta, okay? So if you have this component of the Cauchy stress, to compute the torque, we would first of all we would notice that if you, I don't want to make I don't want to spend too much time into a topic that you may have already seen in other courses, what it is the definition of a torque. But let's say if this is a distance r, then the torque m, which is of course a vector, but it's a scalar vector along the axis, but it's a scalar component, would be computed as the integral over the upper surface of the elementary force sigma z theta times r times dA. So essentially this little piece here, sigma z theta times r, would be the torque per area unit. Imagine, because you see this is a force per area unit, and so if you want to compute the torque, the couple of this force relative to the center, the axis of the cylinder, then you multiply times the arm, the distance. So if you do this calculation for a Mooney-Rivlin material, this becomes 1/2. I just give you the result because I really don't want to make it too heavy. But if you do this for a Mooney-Rivlin material, then you describe that this is equal to C1 plus C2 pi a to the 4th power d. So you see, this tells you that the amount of twist of the cylinder is linearly proportional to the torque. The twist and torque are in linear relation. So which means that if you increase d, which is the amount of twist, you increase m, and they increase linearly. So you see, from this expression you can also, let me say, compute d and find the actual force of compression as a function of the twist. So if you want, you can use this last expression. Imagine an application in which you want to know what is the twist d due to a certain torque. Well, you just have to take this expression and divide mt by this other object here, which is equal to, 1/2, let me just put it in bracket, 1/2 of C1 plus C2 pi a squared, okay? So if you want, this is the other way around, yeah? So there are a lot of materials for which you can do these experiments, and Michel for sure has talked about experiments in which you take little slabs of brain, for example, and you subject them to a torsion, and from this expression you measure the torsion, you impose a certain torsion, you measure the twist, or the other way around, and from these experiments you find the value of the constants C1 and C2. So if, for example, you take an experiment once again and you can measure the normal force and the torque, you have access at C1 plus 2C2 and C1 plus C2. So you see, you have essentially the way to reconstruct from torsion experiments the value of these two constants. So You can also think of these concepts that I've given in this lecture as a tool to reconstruct the material parameters, for example C1 and C2, through torsion experiments. Take a little piece of material, you put it into a machine that does torsion and at the same time can control axial force. You measure the axial force, you measure the torsion, and you can deduce the two constants. So this is a very important protocol to assess to what is the good material, for example, to assess the constitutive model that you can use to model, for example, a gel or a rubber or a piece of silicon, or once again, for example, to simulations that you do for the brain. And this is, by the way, what Michel really does in his own experiments. Now, in the remaining 10 minutes of this lecture, I want to show you that if your target was only to show that the cylinder elongates upon torsion, there is a shorter approach that doesn't require at all that you know what stress is. So let me show you this approach. It is an approach that we have exploited with Michel for a little article that we did this year. And so it is based on the concept of energy. So energetic approach to the Poynting effect. Now, what is the idea behind this energetic approach? The idea essentially is very quickly the following. You know, when you have a spring, and imagine that, for example, you elongate a spring. I'm doing a very quick, very simple application here. So imagine that I subject this spring to two forces, F and F, and the spring elongates of an amount x. You know perfectly that the force in the spring is equal to kx. Okay, now this is a fact. I mean, we know this very well. However, you could find the this relation also in another way. The equilibrium x, minimizes the energy, the so-called total potential energy, given as follows. So this energy is written as, well, U equal to the elastic energy of the spring, which is equal to 1/2 of kx squared, minus the work done by the force, Fx. You don't have to remember these things. It's just this is just a supplementary thing. It's just I think very nice way to see the Poynting effect. Now, in fact, it is easy to show that at equilibrium, the force and the elongation must be related by this expression. This is immediate, because if U has to be a minimized, then you have to impose that the derivative of U relative to x has to be equal to 0. If I compute this, you obtain that this is equal to, well, when I do the derivative of this first guy, you get this is equal to kx. When I do the derivative of the other one, you get f. And so you obtain that f is equal to kx. Now, this little idea can be used to prove the Poynting effect in a rather very, very fast way. And let me show you how it works. Well, first of all, let's apply the same idea. Let's apply the same idea to the cylinder. Now, of course, now I want the cylinder to elongate. So I have to change a little bit the class of deformation with respect to the one I gave you before. So let me imagine that the reference configuration of the cylinder is this. So imagine that this is exactly the cylinder I was considering before. And imagine that in this configuration, the height of the cylinder is capital H. And imagine that upon application of a twist, this cylinder now elongates. Now, a little thing that is, you will see in my drawing, but it introduces a physical expectation. The cylinder has to be incompressible. So if the cylinder is incompressible, if it shrinks, if it elongates, for example, we don't know if it elongates. I mean, I'm just assuming it elongates, but calculations could tell us the other way around. Well, if it elongates, clearly the cross-sectional area has to reduce, right? Because the volume has to be the same. So essentially, let me impose that this upper face here, so from here, let me say exactly the same notations we've done so far. So let me say that, for example, the upper face rotates of an amount d. Now, in this case, the class of deformation is defined by the following, and I will give you directly the result, but it's very easy to deduce it. So little r is equal to square root of h over h capital R. Theta is equal to capital theta plus d z, and the lowercase z is equal to h divided by capital H, capital Z. Now, in this problem again, d is prescribed, d is given, just like in the previous case. So, I want you to do a little, very little application of the things that we did in the previous, in the solution of the previous problem. Compute f, and after you compute the gradient of deformation, compute C, the tensor F transpose F. And when you compute these, compute the first invariant. And this invariant, in fact, it will be equal to 2 capital H over lowercase h and plus h squared divided by capital H squared, and then plus the radius r squared d squared divided by h. So, of course, in all this discussion, little h is unknown, okay? So, essentially, all the other dimensions are given, but the current height is unknown. So, in this expression that you see for the first invariant, everything is known but lowercase h, okay? So everything is known in this expression. Well, at this point, you can use the idea of energy to compute the strain energy. And assume, for example, that the material is a simply Neo-Hookean. So let me take a Neo-Hookean material, and for a Neo-Hookean material, then the energy W is just equal to mu divided by 2 I1 minus 3, okay? And well, once you have the strain energy, in this case mu is the shear modulus and is always positive. Once you have these, you can compute the energy. The total energy is exactly the energy that I was discussing in this example of the spring. And when you compute this energy, how do you compute this? Well, this will be the integral, let me say, over the region occupied by the cylinder. Let me just call this region B, which would be this region here, of the strain energy in dV, okay? And I remind you that in this case, the dV is, well, this will be what? Well, the dV is, it depends on, you see in this expression, the invariant only depends on, essentially, the only variable involved is R. So exactly as in the previous example, when I was computing the torque, this elementary volume here will be 2 pi r, and then times dr, and then times the height of the cylinder. All these happens in the reference configuration. Now, there's a little bit of a very short calculation to do, and what you find is the following. You find that the final expression of the energy of the cylinder can be written as only a function of h. And this expression, by the way, becomes very simple, and I just copy here, but it's simply mu pi h, capital H, all this is fixed, And then here I have 2 capital H divided H plus H squared minus H squared minus 3. All these quantity factors, the radius of the cylinder divided by 2 plus D squared A to the 4th power divided by 4H. Now, what's the idea behind the energy minimization? The equilibrium, remember that in this expression, D is prescribed. Okay, so essentially in this expression here, the only unknown is represented by the current height. How do you find the current height of the cylinder? Exactly as in the case of the spring, you simply impose that the first derivative of u is equal to 0. So you see, it's absolutely incredible how simple is this approach. So let me impose that u prime of h is equal to 0. Well, if you do this, I don't want to bore you with all the calculation, but it is very simple. If you do this, you find a surprisingly nice and beautiful result. It tells you that the current height of the cylinder at equilibrium, this is equal to the capital H, which means the reference thickness, the reference height, the square times cube root of 1 plus a squared d squared divided by 4h squared. Now, for how simple it can be, this expression is immediately telling you the Poynting effect. Why? Look, you see, if in this expression the amount of twist that you prescribe is 0, then this quantity is 0 and the height of the cylinder is equal to the reference height. If d is increasing, which means you are twisting either ways, this way or the other way, it doesn't matter because there is the square, this quantity is higher than 1, and then h, reference thickness, is factoring a number larger than 1, so h is larger than h. Lowercase h is higher than capital H. And this is a proof, a very simple and surprising proof of the Poynting effect. Okay, I think I will conclude this lecture here. I think it was rather interesting to show you the fact that sometimes by using the idea of energy, things can be rather simplified with respect to the case where you need to pass through the stress. You see, in doing this little proof at the end, we didn't have any need to pass through, to introduce stress whatsoever. And I think it is very beautiful because the power of math is synthesis. So if you want to know more and if you want to read a little bit more about this article, there is an article that with Michel we have written on the Applied Physics Journal. So it's called the American Journal of Physics, American Journal of Physics. And look for the article, The Poynting Effect. And this is an article that we did with Michel, and it describes the whole story in detail, and it tells you also some nice historical references on this very interesting problem of elasticity. Okay, I think this is all for this week, and I will record, I think already record the lectures of the next week now, and most likely I will post them earlier than the due date. Okay, that's all, and I wish you to have a good day. Bye bye.